Okay, so we're going to talk about electron tomography theory here. I'm going to start a little bit with why do we even want to do this. And you all know me. My name is Peter Ercius. I'm from the Molecular Foundry, which is a user center in Lawrence Berkeley National Laboratory. And if you come out there, you can work with me on the microscopes to do all the stuff that you are going to see. We have a few microscopes there that can do electron tomography. Okay, so why do we want to know? Why are we taking these pictures of all of these objects at high resolution? What are we trying to do here? Okay, I'm taking a step back here to try to motivate why do we want to see things in 3 dimensions. We already have these really great microscopes that can take beautiful pictures at high resolution. We can see atoms. We can see where everything is. So what's missing? What's left to do, right? So what the key concept here is that structure directly affects functionality. And this has been a long-term thing that people have known. And now going down to the nanoscale, people really need to know what the structure of their objects are at these extremely high resolutions in order to figure out how are they useful, what do they do, and how does the structure affect how they affect the world, basically. And there's a couple of examples of that. You can think of quantum dots or nanoparticles. They're basically called the same thing now. So just a while ago, like in 2010, there were people starting to come out with these. They were able to control matter on the scale of these nanoparticles at 1 nanometer, 2 nanometers, 10 nanometer type things. And one of the first things that they did was just by changing the size of a different type of quantum dot, you could get, and then you suspend them in a liquid, you could just change the color of them, even though they're the same material. So it's not that these are emitting light because of the material that they are, it's because of the size that they are, okay? So that's a really good motivation for why do we need to look at these nanoparticles. We don't just want to look at them in the macro scale. We want to look at those nanoparticles and say, why is this occurring, okay? And then this seems cool. Like maybe you can make a cool, these liquids look really nice and it makes a nice picture, but why are they really useful? So what they use quantum dots for, one of the many things they use quantum dots for, is for tagging in biology right now. So all these people are doing super resolution and imaging things at extremely high resolution in cells. And light microscopy is really good for that. But in light microscopy, the cell, like everything, is extremely complicated. But if you can get these quantum dots at different sizes to tag to different parts of the cell, you can make those light up by shining different light on them or by filtering out all the different light so you can see where all the different parts of the cell are without all the other overlapping parts. So they're very good at tagging, using these nanoparticles to tag things for medical imaging. Another thing is people started making tetrapods. So you can make objects that are not really that are not symmetric. They're not like round. You can make them with all kinds of different shapes. And just by changing the shape of these and the size of these different wings, you can get all kinds of different absorbance spectra out of them just from their shape. So these are just 2 examples of basically all of science of why people are changing the structure and then trying to affect or use those properties of the structure to measure things or to use them for something, okay? So the problem is that what we have in a lot of these things, I showed you some 2-dimensional pictures of things, right? In an electron microscope, we have a source. We have our object, which we can't really see. And what we really have are kind of shadows on the wall. It's a transmission mode, right? So we see what goes through the sample. But you don't really see what the actual object is. You see an image of that object, okay? But what's in between here might be very different than what you see on the screen, okay? This is all tomography people use this picture from the New Yorker magazine. And for a long time, people didn't reference it properly. So now, thanks. Rob told me, you got to reference that. So this is basically what we're trying to do. What you see in the microscope and on the screen may not be exactly what your object is. You can get fooled by these projections, okay, very easily. And so how do we go towards getting these 3-dimensional images? And a long time ago, the biologists figured this out a really long time ago. They figured out that all these objects that we're trying to look at, they have a structure to them, and that structure is how they operate in our bodies. But the beauty of biology is that it can be replicated over and over and over and over, right? That's why we're all alive. That's why we all live, right? Because biological structures are homogeneous, okay? They're copied, and so you can basically take these structures, and because they operate the same way in every single person, you can copy and purify those, and then you can take images that look like this, where you can barely see the structure of any of it, and you average many, many images of these. So you look at a sample that has a purified structure, and then you can get a nice 3D reconstruction from that. So the problem in physical science is that we can't do that because materials, nanomaterials, are different at the atomic scale. Every single one is a snowflake, okay? And that means averaging is pretty much right out. You can't get a lot of information and figure out what these structures are just by averaging. And if you look in literature, a lot of people will say they have monodispersed nanoparticles, okay? But then they show you this, which is their histogram of the sizes of those nanoparticles. Yeah, okay, they're monodispersed to a physical scientist, but not to a biologist. It's not the same level, okay? So we need to look at things, and we need to look at every single thing as a unique object, and we need to get information from that unique object, extremely localized information. So we must resolve the local atomic structure, or the local structure. It doesn't have to be atomic. It has to be localized directly in order to measure defects, compositional antiphase boundaries, amorphous structure, for instance, where dopant atoms are in these materials. And what's becoming important in almost every level of how things are functioning, like your computer, for instance, where a couple of atoms are in the source or the drain or the gate or anything of a transistor, for instance, or even these nanoparticles, like active core shell nanoparticles, where single atoms are in these objects is important. Whether they're in the center, dispersed, clustered, but that's very, very important. So getting two-dimensional images like this is no longer, it's very, very useful, but it's not the end game. It's not what you really want. Okay, so we need to be able to do tomography from the micron to the nanometer to the atomic scale to really figure out what's going on. And so what I like to say, and I heard this in another talk by Alex Little, if you can measure it, you can make it. Because if you can't see what you're looking at, if you can't figure out what the structure of the thing is, then you just are blindly throwing things on the wall and seeing what sticks, right? But if you can measure it, then you can figure out, I changed this parameter and make this structure. So this is why we're doing all of this stuff, okay? So how to get to three-dimensional structure. Tomography isn't the only game in town. It's been around for a long time, but it's not the only game in town. So I want to say there's many different ways to do this, and they all have their own strengths and weaknesses, okay? So X-ray crystallography was one of the first and one of the most powerful. So what you do is you take a crystal, you shine X-rays through it, and you get a diffraction pattern, and then you invert that diffraction pattern. So the problem is this has to be homogeneous. So this works really well for proteins. It does not work very well for nanomaterials. Cryo-EM is what has been something that's been going on for a really long time, and I told you a little bit about that, where they take these exactly the same objects. These are viruses. They purify them, they take images of them, and you can get a three-dimensional reconstruction by averaging thousands to tens of thousands to hundreds of thousands of images of these. And it's called single particle reconstruction, but that means taking many particles and making them one single particle. So it's a weird way to talk about it, but that's one way to go. And this is becoming, for various reasons, this is becoming the technique nowadays because of that K2IS that you guys saw and you will get to play with a little bit later. There's another thing called atom probe tomography, and this is where you make a very tiny tip, and you evaporate or you rip the atoms off of that tip, and then you have a screen where you measure how long it took for those atoms to hit the screen, and by assuming the shape of the tip, you can figure out the type of atom that is and where it came from. So you can do a three-dimensional reconstruction as you rip this apart layer by layer by layer. The problem here, they only get about 30 to 60% of the atoms, and they think that's a little bit of a limit. Never say that's the end, but there are some assumptions and issues with this, but they can look down to what the dopant atom concentration is of very, very nice things, of things to very high precision, but they still are losing a lot of atoms, so it's not a perfect technique. None of these are. And then electron tomography, this is where you have an object in your microscope, and in order to get three-dimensional information, you take an image of that object at many different orientations, okay? And this is one single unique object. You take images of that exact same object at many different orientations, and each projection gives you a little bit more information about that object. And this is what we're going to be talking about today. Okay? So going back a little bit, why are projections bad? Why are they limiting us? Okay? So if you look at this kind of weird thing that I made a while ago, you just have a box. This is kind of your field of view, and you have these 4 different objects. It's a projection view, right? So are the objects arranged like this? Are they arranged like this? Are they arranged like this? And this has all three of these projections. Like this image, you could not tell the difference between these three things from just one single projection. So it's very important, like whether this nanoparticle or something is inside the cell, that makes a big difference as to whether it's inside or outside the cell, right? So what we're going to try to do is try to get a reconstruction where we can tell the difference between an object on the top, on the bottom, in the middle. And from a projection, since we see through the whole object, we're not just seeing the surface, we can do this. We can actually take our object apart after we reconstruct it. You can see inside the object. So electron tomography is a method in which a higher dimensional structure is reconstructed from a series of lower dimensional projections. Okay? And that's usually by sampling the structure from many, many different directions. The original description of this was from a long time ago, a 1917 paper. It's been originally developed for astronomy, and then it was more commonly used in what's called a CAT scan. That's where you take an X-ray source and a detector and they spin it around you, if you've ever had the misfortune of having to have a CAT scan. So it's actually called, a CAT scan is a computer-aided tomography. And they left X-ray out of there because they didn't want to tell anyone they were X-rays, I guess. So any series of projection images then can be utilized. Okay? So you can look for inspiration in electron tomography, how to do reconstructions, how to do visualization, how to do segmentation, which is all these things we're going to talk about. You can look in many of these different fields. I'd say TEM is not as developed in tomography as some of these other different fields. So there's a lot to be learned from astro, bio, medical imaging. The problem is medical imaging, they're all billion-dollar companies. They don't want to tell you what they're doing. But we're catching up. So a tomography experiment. There's two parts to a tomography experiment. Actually, there is a third part, which is equally important, but these are the main two ones that I'm going to talk about. Rob will be talking about the third one. So acquisition and reconstruction. For acquisition, I talked about it a little bit already. For acquisition, you take your object here, and we do many different images of this object at many different orientations. For a CAT scan, they keep you centered, and they spin the detector around you, because you don't probably want to be rotated around like this. It's not the way to go. But what we've gone to is great lengths is to make our electron microscope extremely stable, right? We have this source and this detector, and you're not going to spin that electron microscope around. So we spin our holder around, our object inside, right? So we try to acquire many different images from many different tilt angles, okay? And there are various limitations to this. And then this can be done in astronomy, TEM, medical X-ray, all kinds of things like that. It's the same exact thing, okay? The next thing is the reconstruction. So you take all of these images at many different orientations, and in the computer you have to line all of those images up, because every time you move your object, it moves a little bit. Then the computer tries to bring it back, but it's not perfect. So as long as a thing is in the field of view, you can reconstruct it. And you use the computer to back project, or kind of you project these things back at the different angles, and from that you get a three-dimensional reconstruction, which is the whole lecture that we're going to talk about today, basically. We're going to kind of skip this, because this is automated now, at least for nanoscale tomography, and things can be set up on the microscope, and you can get this tilt series without too much effort right now. This is where the real problem is. This is the bottleneck. Okay? Alignment and reconstruction. So we need to know these viewing directions very precisely. Okay? And then we also need to know something that our projections are a monotonic intensity of some sort of measurement of the object. And in most cases, you want to think of density. Okay? So this is really critical. It needs to be that when you look in your image, each pixel in that image, the intensity in that pixel, is a measurement that doesn't change randomly as you tilt the beam. Okay? So as you tilt the sample, not the beam, as you tilt the sample. So as you tilt the sample, the object changes a little bit. This becomes thicker, this becomes thinner. You have less intensity here, more intensity here. And then you can use electron tomography to reconstruct that. And we'll talk a lot more about this later. So this is called the projection requirement. Okay? Projected intensity must be a monotonic function of some property of the object. Mass, thickness, you can do electric potential, you can do magnetic fields, lots of different things. But what almost everybody does is kind of the mass thickness. It's the mass of the object, okay? So a really simple way to think about it is something called Beer's law, which is a good law, for scattering is exponential with thickness, okay? So you think of the intensity in your pixel is some exponential function based on the thickness and the cross-section, the elastic cross-section in this case, multiplied by your original intensity. So it's the original intensity that hits the sample, and then you get less or more intensity as it goes through. Okay? So TEMs are, in fact, structure projectors under certain conditions. TEM, if you put it in an objective aperture, you can enhance what's called amplitude contrast. That's basically electrons that scatter so much that they leave the electron microscope. They scatter beyond the resolution of the microscope. They hit the aperture, basically, after the sample. So that's amplitude contrast. But we don't use TEM in physical sciences because usually for crystals, the object will flash on and off. And you'll see that very clear. Like if you look at nanoparticles, you'll see that this one's bright and this one's dark, even though they're the same exact size. And when you start tilting things, it gets way worse. Okay? ADF stem, though, is incoherent. Generally, if you're looking at an object and it's bigger or thicker or has no more mass in it, it has what's called Z contrast, right? Or thickness. It's also thickness contrast. And it doesn't change as you tilt the object. This is exactly what we need in order to be able to reconstruct our objects. TEM is used a lot more in biology because they have amorphous, blobby things, squishy things. And ADF stem is used in material science. OK, so a projection operation. You have some object that has some, it's a function, let's call it a function, where at each XYZ position, you can describe that as a density. OK? So an object's density can be discretized as a function within some sort of, we call it a voxel. A three-dimensional pixel is called a voxel. So if you project this using some sort of projector, a projection is similar to a summation along a given direction. So you just sum this function, you integrate the function, which you can then discretize by summing along some direction. So let's pick z. Let's say we're going to sum over z. So then we get some two-dimensional picture of the object that just has f of x and y. Now, OK? We can do this at any angle that we want, and we'll get a slightly different projection with different ranges of intensity, but it's still the same object. OK? And so we can project at some theta, and our f of theta is some two-dimensional thing. So we're taking something that's higher dimensional, making it lower dimensional. That's what you're doing. OK, so let's just look at 3 projections at low tilts. OK? Each one of these, let's just say each one of these is an image. And this is our original object. It's really simple. 3 dots. If you were to just look at one projection of this, you'd say, I know the distance in this direction between these 3 dots. You have no idea they're out of plane from each other. Right? But if you start taking projections at different angles, you see that these 2 dots become closer together on this side, and these 2 dots become closer together on this side. That means they have to be at different z heights. OK? So just by each tilt that we take gives us a little bit more information about the distribution of density in this object. OK? So doing that projection is one way to do things. But what we're actually going to be doing is you can think of things in terms of density in real space, but you can also think of things in terms of frequency in Fourier space. There's not just a 2-dimensional Fourier transform. There's a 4-dimensional Fourier transform. You can do it as many times as you want. Okay? So if an object has a mass density of f of x and z, let's just say it's a 2-dimensional thing. Okay? If you take the Fourier transform of that distribution of density, okay, that's an integral. This is the definition of the Fourier transform. And so you're taking this f of xz, and if we kind of break this out, okay, and we can move our dz inside here, and we can just write this a little bit differently, right? This, we're actually looking at an integral of f of xz over dz. That's exactly the same as a projection, a summation of the density along that z direction, right? So we're trying to say that our object in density has a Fourier transform, which is an equivalent way of describing the object. They're exactly the same. Okay? It's the same object, just different basis set. Okay? So, but if we write the function that we'd normally look at in a slightly different way, you actually can start looking at what the projection is. So this is the Fourier transform of the projection in the end. So if you're doing a projection and you take the Fourier transform of that projection, then that is equivalent to taking a slice of information from the 2-dimensional Fourier transform of this object. So instead of having an object with densities all over the place, you actually look at the Fourier transform, and you just sample that Fourier transform where each one of these dots is. And that is the same thing as doing a projection operation. So you can sum in density. You can sum the density. Or you can just sample the Fourier transform. They're exactly equivalent. And that's known as the Fourier slice theorem. So this is a way to think of how our different projections of our object build up a three-dimensional, or in this case, two-dimensional, all the information of the object that we want to know in order to figure out where is the density of all the objects. Okay? So let's think about this in 3 dimensions instead. Let's make our object 3 dimensions. So we've already said that a Fourier transform of f of xy, that's what this f of kx, ky, right? So now if we make it 3 dimensions, we just do a 3-dimensional Fourier transform, and that just gives us our 3-dimensional space, the frequencies in 3 dimensions rather than 2 dimensions. Okay? So each one of these projections then, in real space, at an angle, gives you some density, or some integration of the density, a projection, right? We take the Fourier transform of that projection, okay? And that's equivalent, as I said, to this sampling of the Fourier transform at some angle. This angle here and this angle here are the same angle. So if you're doing it at 0, then you're just looking at what the distribution is only along kx, and you have no ky. But if we tilt it, then we get a little bit more information out of that plane. So you can see that if we are sampling the Fourier transform of the object at different orientations, as we change the orientation of the object, we get a little bit more information of the object every time we tilt. So we're starting to fill in the 3-dimensional, or what we're doing is we're sampling the 3-dimensional Fourier transform of the object. That's exactly what we're doing when we're projecting things. Okay? So just by rotating the object, you get different sampling of the Fourier transform. So how does this really work? So in real space, we can just think of an object like a square. Okay? It's 2 dimensions, and I'm just going to sum along this direction. Okay? So at 0 degrees, if you're to sum, you have 0 here, and then you sum through this. It's about 256 pixels. So we get 256 as we sum through this, right? Because there's 1 in each voxel is 1. So this gives us a thickness of the object of 256 along every single pixel along this direction, every single column this way, right? So now if we change the rotation of that, we can see how the object, the information we get from our different projections changes. It's no longer the same shape, right? We can get something else. And so each one of these corresponds exactly to just sampling that object along different orientations, along exactly the same place, okay? And I can show you that. I can show you that in the next couple of slides. But critical to the understanding of electron micrographs is the reciprocal space formulation. So I just told you that many, many times over, but let's look at that a little bit more in detail, okay? So it's equally referred to as Fourier reciprocal frequency space, right? You might hear that many different times. So the Fourier transform deconstructs a real space object into spatial frequencies. It's a set of cosines and sines, which, if you remember from your math. And then this is critical. It's one of the most important things that you can understand about images, about electron microscopy, about tomography, everything, is to have an intuition or have a knowledge of how the Fourier transform is extremely useful. So one key distinction between real and reciprocal space, which is a good concept to keep in your mind, is that things that are extended in real space are then compressed in reciprocal space. And things that are compressed in real space are then extended generally in reciprocal space. Okay? And that the diffraction pattern, you can see that directly in the diffraction pattern from a TEM or a STEM, for example. So in a TEM, you have a parallel beam of electrons, and your diffraction pattern has dots in it, right? In a STEM, you have a converged beam of electrons, and you get disks. So that dot, you're looking at a converged probe in STEM, and in your diffraction pattern, you get disks, so it's extended, something small to something extended, right? But it's the opposite in TEM. Something that's extended is then very small. Just a nice kind of concept to keep in your mind. So let's look at just some images and look at the Fourier transform of those images, and just from kind of an intuitive imaging kind of way, let's think about what this tells us. So when I am on the microscope, I take a Fourier transform of almost every image I look at, because I can look exactly at the quality and what is going on, whereas I have no idea kind of what this means. You can see where atoms are. This is actually graphene taken in a normal HRTEM. It's an aberration-corrected HRTM. But here, if you take the Fourier transform of this image, you see dots, right? And so what are these dots? These dots actually tell you the distance between all of these atoms. So each one of these dots is an average over the entire image, gives you an average, right? So even though this is quite noisy, you can get information where you might not even be able to see something in your normal image where you would see a spot in the Fourier transform because it's averaging over the whole thing for you, telling you where the information is. Okay? So the spots are also farther from our 0, 0 dot. As we go higher, k, that means that you're getting to higher frequencies. That means you can see things that are smaller in real space. Something that's smaller in real space will be extended in Fourier space. So things that are out here, information that's out here, that means it's higher frequency or smaller things, smaller spacings. And it's the exact opposite. Lower frequency here means larger things. Okay? So if we look at, for instance, let's look at this HRTM of 2 layers of graphene. This is a Moiré pattern, or it's pretty much a Moiré pattern, and you can see different atoms in different places. But if you take the Fourier transform of this, like you might not be able to tell the difference between whether this is 2, 3, 4. You have no idea what this structure is. This is graphene. It's like, that doesn't look like graphene, but you know it's in there. So if you take a Fourier transform of this, you can actually see the 2 different spots, and you can measure exactly the rotation of those 2 graphene sheets, right, from just the distribution of these spots. So just by changing how you're looking at the information can tell you a lot more about the object immediately, just by looking at it. Okay? So this first ring of spots in the center here is equivalent to the 0.213 nanometer spacing, which are 4.7 inverse nanometers from this center spot. Okay? Those. But then the second ring of spots, that's the distance between one of them is the distance between the carbon atoms, like that 6th ring, right? It's that pattern over and over. And then the further out one, the second further out one, is the 0.123 nanometer. That's the distance between each carbon atom. Okay? And so just from this, we can figure out that this is graphene. It's not tungsten disulfide. It's not something else. And we know that there are 2 sheets, even though from looking at this, we have no idea what's going on. Okay? So I'm just kind of motivating you to look at the Fourier transform and to think of things in Fourier space. It can be very, very useful. And for tomography, it's extremely useful as well. So anything, you can take an FFT of anything, right? Your computer lets you do that. So this is a picture of my dog, Taco. And just try to break things up. It doesn't all have to be science, right? So this is a dog, and this is the FFT of that dog. So you can look at this. You could look at this and make some assumptions of that she's extended in this direction, so there's kind of information along that direction. So just by doing that, you can look at things a lot, and you can process things a lot on this, right? So any object or image can be composed of a set of spatial frequencies. Okay? So that also means that we can think of tomography as a set of spatial frequencies. So each image can be represented either way. It's completely equivalent. We're just used to this one. I'm now maybe a little bit more used to this one. So also it's important to know that the FFT, this diffractogram, tells you the average information from a specific frequency over the entire image. So it's really nice that you can, things that you can't see in an image at really low dose or something, you might be able to see in a Fourier transform and be able to see, I can see that spot is there. Because what we can do is these discrete images, they're not images at all. These are data sets. That's a very important concept. Okay? If you zoom up and you look at just a little piece of this, it's just a bunch of pixels, right? This picture of my dog is a bunch of pixels. So we can treat them equally, and we can use them as data rather than images, where you just look at it and you say, yeah, I think I see that. But now we're going to use things as data where you can say, I can use this to extract more information than just visually what I see. Okay? So this becomes very important if you're thinking about tomographic reconstruction. Okay? So in a reconstruction, if we go back to the beginning, we already have our tilt series. Okay? So we have all of these different images at many different orientations, and we use a computer to back project those images, which I'll get to later, and create a model of where the intensity is and what the object's shape is in 3-dimensional space. And since we have that in a computer, we have the inside, we have the outside, we can slice that then along any direction. So even if you took images from 0 to 40 degrees or not that many images, you would be able to look along almost any direction that you want. It doesn't have to be orthogonal. You can look at all kinds of weird directions. Okay? And the computer, you don't, the way that this operation works, you don't have to see a specific thing or be able to see it in a certain projection image. Like you don't have to see a certain lattice spacing in projection image or a certain shape of a certain object in a projection image. Or if 2 objects overlap each other, you don't have to get it such that they don't overlap. You just don't have to worry about that. The reconstruction algorithm will take care of all of that. Just get images that are projections and do the alignment properly, and you'll get a 3D reconstruction. The computer takes care of that. Okay? but it's good to know what that block box is doing. So you have to fulfill the projection requirement in order for that to work. We have to get accurate spatial alignment. We need a determination of the tilt axis, how the object rotated. And then we need accurate angular increments, because if you're at 5 degrees and it thinks you're at 10 degrees, that's not going to work at all. So if we look at, in 2 dimensions, our sampling. So we know that each image that we take is a sampling of the 2-dimensional Fourier transform, or in the case of just a 2-dimensional image, of a two-dimensional slice. But really what we're going to do is 3-dimensional imaging. So now instead of just ky and kz, we have kx, ky, and kz. So this is what it really looks like. This is what you normally see, because it's simpler. But this is what it really looks like. You're missing this gigantic wedge of information, because we can usually only get up to about plus or minus 70 degrees. And even from, this may make you a little bit worried, but even from this, we can get really good reconstructions, although we have a bunch of missing information. But this is what you're really looking at. So you get all this sampling of this image very well along one direction, not so great along y, and then not very good at all along z. Where z is the direction you really want to know the information. Because you already have kind of this, you have kx, ky from one image, but you really want to get to as high a tilt angle as you can, because you need this information up here to tell you how the thing looks along that projection direction. Okay? So the resolution in your tomography, your x is similar, assuming that you do a perfect alignment, to your image sampling. Your y is connected to the number of tilt angles that you do. And your z is connected to the max tilt angle that you do in general. Okay? So if we think about where does that come from, why does that happen? Okay? If you think of this is our 0 frequency, and we can go out to some sort of frequency out here that gives us some spacing. Because we can think of inverse, or a spacing inverse here. I told you that like in the Fourier transform we had 0.213 inverse nanometers, right? It's the same thing as, I think it's some 4-angstrom or something. So this dy, then, because we're discretely sampling a continuous function, right? Because we have these different projections along different angles, we only really kind of overlap those projections, right, to a certain outer degree, right? So we're sampling. You can see we actually oversample here because we have, these are very, very close together, these 3 projections. But as we get further and further away, those projections know less and less about each other. They're less connected to each other, right? So this overlap is kind of set as the maximum resolution that you can do along that direction, because you've discretized the sampling of this information along that direction, okay? So this is kind of, if you know about the missing wedge, this is kind of the unknown missing wedge, the little mini missing wedge between each projection, okay? And so that dy is a lot, kind of your resolution along that direction has to do with pi times the size of the object divided by the number of projections that you take, okay? So that's due to the discrete sampling of a continuous function. So this gives you an idea, in an ideal case, what your resolution will be along the y direction. Okay? And so if we think of dz, this is connected not only to dy, but it's also connected to the maximum tilt angle you get. And so by thinking about the maximum tilt angle that you get to, which is the missing wedge, you can work out what the elongation along the z direction is. So you get non-isotropic information in your 3-dimensional reconstruction, which is not great. But you can take, as long as you know that that exists, you know which direction it is, you won't be fooled by the artifacts that we're going to show you later. So it's really important to know which direction you're going and what you need to accomplish. So these kind of give you an idea of that. These are not set in stone. This is not your final resolution. But this gives you an idea of what to shoot for. These are idealized, okay? So I probably talked a lot about that. But if we think about, you usually take about 1 degree, maybe 1 to 2 degree tilt steps. And that's because we need to fill in Fourier space, because we need to sample these pixels in Fourier space out to a certain resolution, right? And by doing 1 or 2 degrees, that gives you a pretty good sampling up to a given resolution, okay? So that's why we do 1 or 2 degree tilt steps. Going much further than that is not really that useful. And going less than that is also not that useful. So that's kind of the sweet spot. If you do dz, the elongation, if you get up to 70 degrees, plus or minus 70 degrees, you have an elongation of about 1.3 along the original projection direction. Kind of sounds not that great, but you can really see the shape of objects when you get up to about 70 degrees. If you're not quite up 65, 70 degrees, you probably shouldn't do it. And then the electron dose generally limits the applications of all of this for dose-sensitive materials, almost any material. We have to take 70 to 140 images of the same object, and that's only the images that we put in the tilt series. We're not talking about tracking, focus, everything else that we have to do. Okay? So the electron dose is really what limits you in almost all of these cases. All right? For biologists, that's extremely correct. And in material science, you might not think about it, but it is one of the things you really have to do. So always take an image before you do your tilt series and after. That's a really good thing to do. OK, so now that we have sampled Fourier space, right, we have all of our tilt images, and we understand that we kind of just have to take, do we just really have to take the Fourier transform of our projection, put it in Fourier space, put them all together in the right way, and just do an inverse Fourier transform? What do we do in order to get the three-dimensional reconstruction of our object? Okay? And so can we just invert, why don't we just inverse Fourier transform this? All right? So does just applying the inverse Fourier transform produce our object? And in theory, that would work great. But there's a problem with how the math works out, in that what we've done is we've sampled our object on radial coordinates, right? R theta, distance from the center, or sampling, and at each angle, right? So each one of these dots would be that's the frequency that we measured at a given angle, right? And that doesn't map perfectly into the Cartesian space of our reconstruction algorithms. Most of them work like that. The FFT works on Cartesian, xy. So by doing some, you can do this. You can figure out that you can interpolate these measurements, each one of these dots, into the dots that are in Cartesian space. But the way that you do that can be very complicated. And it can be slow, and it can be very difficult to do, and you can get artifacts very quickly. This was true years ago. Computers and people's algorithms have gotten much better. But generally, the algorithms that you would have access to, that you would use, like generally that are available in most of the reconstruction packages, don't use this kind of inverse Fourier technique. They use a different technique, and that's because this interpolation it can be very difficult to do, and if you don't do it right, you can get a completely wrong answer. So there's an easier way to do this. Okay? But I want to say that newer methods do solve this problem, and that's the future. Those are going to be available eventually. Right now, they're mostly in papers, I'd say. So the radon transform is how we get around this. We don't go into Fourier space. We don't have to go into Fourier space. We don't have to deal with that, the Fourier transform. We actually go from the image domain into what's called the radon domain. So a lot of people say it stays in real space, but it's not really staying in the same real space. But there's just no Fourier transform involved. Okay? So a projection through this object, if we sum along this line, that's what we're doing, right, of this object, where that line is some distance rho from the 0, from where we rotate the object, right? And you'd think we'd have many, many projection lines, but let's just look at one of them to keep it simple, right? So we sum over this blue line, and that gives us on our rho theta axis, which is now radon space, instead of xy, we go to rho theta. That gives us one value for that projection. All right? So this is one measurement at r of theta comma rho. All right? So no Fourier transform is used. This avoids this amplitude and phase issue, and there's much simpler interpolation. So what we do when we're going to back project, when we're going to get our 3D information from this map, we're going to have to find out what pixels are in between these measurements, and it becomes much more simple. Okay? So this is what an actual sinogram looks like. And they call it a sinogram because things look like sine waves. Because if you're rotating something around something else, it kind of looks like a sine wave. Okay? It'll go like this. So these are actually the densities, the projected densities, and I can tell that at an angle theta equals pi over 2, I know that at this row, I can tell you what the projected density was of that. Okay? So now what we're going to do, if we go back to this, we see that this simple sum of the mass at each tilt projected onto a line, that gives us these different measurements, right? Each one of these is really a density, not kind of the location of the object. And that goes right into the sinogram. So each one of these projections then, you can take this value and put it right into the sinogram. And so how do we get our information back out of that sinogram? And that's what's called back projection. So you take each one of these measurements of the intensity, and you say, well, I know my object has to be somewhere along that line. This amount of density has to be located somewhere along that line, back projected into the 3D space at this direction, right? It's like shining a light onto it. And then if you were able to build a whole bunch of lights or something that all came from all of our different projections, all simultaneously, right? You can figure out, like, I don't know where this density is, but it's somewhere along this line. But this one says, I know that there's density along this line. So you can see that you start building up where this one knows that there's no density here, but this one doesn't, right? So each one gives more information as you tilt. But you can see that if you don't have enough tilts, it's very easy to get some artifacts, right? So all of them thought, maybe there's actually 5 lights. There's not 3, okay? But if you start getting higher tilt angles, right, then you can say, I know these don't exist, right? So that's how back projection really kind of works intuitively, all right? So many projections allow a reconstruction of very complicated objects. If you only have a few objects, if you only want to see where objects are in space, sometimes you can do that from just 2 images that are tilted from each other, right? If you know the center, like those objects are nanoparticles, you don't care about their shape, you just care about their location. You don't need to do tomography. All you need is like 2 projections, right? From different angles, because then you can work out. That's how we do everything, right? With 2 projections. But if you have many projections, then you can start looking at the inside and the shape of these different objects, where all that density is located. Okay, so the inverse radon transform then takes this sinogram. This is a much simpler sinogram now. I have one nanoparticle, let's say, that I took at many different tilt angles, and I projected that nanoparticle. And so at different tilt angles, you'll see this object, because it's away from the tilt angle, right? From the tilt angle where we rotate it, it will rotate. The projected object will rotate around like that. And its distance from, you can read off basically its distance from that tilt angle, that tilt axis is what I want to say, just from the rho axis. So if you give a certain theta, certain rho, and what the radon transform is going to do, it's going to look at this sinogram, and it's going to say, I need to know in 3D space where this density comes from. And it looks at it. It knows, it should be at rho, this theta, and it picks out what that intensity should be, and it puts it in those voxels. All right? So let's look at how we build up a reconstruction in real space and in Fourier space, because we want to look at them equally. Okay? So here, let's just back project an object. We don't know what it is, right? But along the 0 degree, we know it looks like this. This is the back projection. So we fill in everything along this axis. So this is actually the Fourier transform that I'm going to show you. This is a movie that we'll see run. This is the projected, this is the 3-dimensional reconstruction of our object as I add different projections in, okay? And you're going to see equivalently the Fourier space representation of that, both together, okay? So you can see, I haven't done any tricks. This is just the back projection. There's nothing having to do with Fourier space here, right? I haven't taken the Fourier transform of anything until I do the reconstruction. So you can see that even by doing the back projection, which doesn't go to Fourier space at all, it's exactly the same as doing the Fourier transform thing that I was talking about before. So just taking the Fourier transform of your 3-dimensional reconstruction, you can see exactly how it's built up in Fourier space and where you got your projections from. All right? So here now we can tell that since I had enough projections, I can tell this is a square. Right? OK, so what happens if we can't get up to that high angle, right? We can't get plus or minus 90 degrees, which is true in almost every case for many different reasons. And so if what we have is called the missing wedge of information, right? And so that means that as we build up our reconstruction is going to be missing information. And how does that affect the reconstruction, right? So let's look at this movie really quick. And we can see that as we build up our object, we have to stop at plus or minus 70 degrees. And now we can't really see that this is exactly a square, right? So this is an artifact, and this is kind of one of the worst artifacts you could see, that if you have this object here, you're missing information about that edge because you could not look at the thing along that direction, right? So you're missing all of this information. You get kind of an elongation of the object along this direction, right? And if you knew it was a square before, you might say, yeah, OK, that looks like a square. But if you didn't, you wouldn't really know what's going on, right? So you really need, the higher you get in tilt angle, the more information you're going to get out of your object. And you can get rid of these. So if we just look at the full reconstruction and we compare these two, then we can see that we get some bad artifacts, right? And this is kind of a worst case scenario. I haven't done anything complicated here, nothing interesting really. So one problem that we can actually say is how do we go beyond this? So that was not a very good reconstruction, right? And there's a reason why that was not a very good reconstruction. The back projection algorithm is not a great way to do a reconstruction. It's the simplest thing you can do, but it's not really smart. So what happens is when we're sampling our object at all of these different orientations, you can see that we have a lot more dots, a lot more samples in the center than we do out at the higher frequencies, right? So we're heavily overweighting the information that we put in our Fourier transform, or that we reconstruct, at low frequencies. Those are things that are big. Those are things that are not sharp. Those are things that are blurry. And you can see that we're missing a lot. This becomes very blurry, right? That's a really hard edge. So that's difficult to reconstruct. So what happens is we oversample things down here at low frequencies, and we undersample things at the high frequencies. So we're heavily biasing towards making something look blurry. But what we can do is called the weighted back projection, where you just say, well, I know what my weighting should be, so I'll just underweight things in the low frequencies and overweight them in the high frequencies. Just with you just make a filter that has a value that's equivalent to the distance from the zero, so how high frequency it is. All right? So this is an R-weighted filter, W, in Fourier space after the back projection. So you do your back projection, and then you just apply this afterwards. And you get much better reconstructions. So this is a phantom, let's just say. This is a common reconstruction test that we use in tomography. So this is the original. You can see there's all kinds of different shapes, and they overlap in different ways. And if we project this phantom along this direction and then rotate it and project it along all these different orientations just in 2D, if we then do a reconstruction where it's unfiltered, we just do the back projection, okay? Just based on the fact, even if we don't have a missing wedge, we do plus or minus 90 degrees, you can see this thing is actually very blurry, right? You can see big objects, but you can't see any of these small objects. And that's because we've overweighted the low frequencies. So you don't see a lot of the high frequencies, you see a lot of the low frequencies. And it's very blurry, right? But if we filter it with plus and minus, like no missing wedge, you can see we get a very good reconstruction of the original object. It's almost perfect. Okay? So this weighting filter is one way to get around the fact that we're not really sampling things properly. And you can't really get around that. Okay? So this filter faithfully reproduces the original. So that's what weighted back projection means. So let's look at still some artifacts. So that was a perfect plus and minus 90 degrees, right? And if we go from the original, and now we actually do only plus and minus 70 degrees of rotation, you can see that things that are along this axis, actually the original projection axis, we get some artifacts. So there's no way to tell whether this thing closes itself or whether it kind of ends here and we get these kind of tails, which is very common that you'll see in reconstructions. These are the things to look for. Okay? So that missing information introduces artifacts that are not seen in the original projections. All right? So, but what we can do is go back to these original projections, and we can use them as a reference to comparatively say, this really shouldn't be there, right? So if you look at your original images, that really shouldn't be in the real space image, right? So we can use our original projections to say, that's not really where that intensity should be. And so that's where we get into the iterative process. All right? We have more information, and we want to use it. So we take all of our projections, we reconstruct something using back projection, okay? We can then, since this is a set of intensities or voxels that are in our microscope, we can actually take this reconstruction, right? And we can project it again. We can do a simple operation where we just sum all the voxels along a certain direction. And we can create a new tilt series, right? We generated from our three-dimensional thing. It's all in the computer, right? So then we can compare how these projections match to our original experimental data. We can use something like a division operator. And by doing that, you can say, like, there's intensity out here in this corner, which is not in the original image, right? And so by doing that, you can get rid of things in real space that aren't really there, right? It kind of adds constraints to the reconstruction. But you need to do this iteratively, because you need to make a reconstruction, reproject it in the computer, and then compare them, and then do it again. You do it again, 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 again. OK? So the iterative algorithms then, for a non-iterative algorithm, you just take the experimental projections, back project, do some sort of, you could do weighted back projection, bam, 3D reconstruction. It's very quick. It can be very fast. It could be minutes. It doesn't take hours in some cases. But if you want to go into the iterative loop where you can improve your reconstruction, you can then project again your three-dimensional object in the computer. You divide these projections by the original ones, you take the difference projections, and you actually use those to do your reconstruction. And you go back and forth in this until you reach some end conclusion, right? Where you say, this is good enough. The thing now doesn't change. The match between my experimental and my simulated projections is matching very, very well. That gives you a final reconstruction. So let's look at this. This is just the first iteration of what's called the simultaneous iterative reconstruction technique, or SIRT. Weighted back projection and SIRT are the things that you'll see in almost every reconstruction code right now. These are the two that you really need to know about, okay? So this one takes a lot longer because it has to do the weighted back projection, or just the back projection, many, many, many times. So 1, 2, 3, 5 times, 20 times, it takes 20 times as long, okay? So this is one iteration, and let's look at how the object changes as we change the number of iterations. We can see that that low frequency kind of blurriness goes away, right? And we actually get a better, let's see, a better reconstruction. It just wants to go to the end. Okay, well, we can't see that again. I don't know what's going on. Okay, so you can see that the object became more and more faithful to the original object, okay? And we can see that if we take the difference between the original projections and our now reprojected things, we can see that the difference between them gets lower and lower and lower and lower as the number of iterations improves, right? But at some point you reach some minimum that you can get to, right? So there are only very small changes in the reconstruction beyond about 20 or 30 iterations. And in some cases, if you have kind of noisy data or bad data, this actually will start going up. It will get worse and worse and worse. So you don't want to just set it to 1,000,000 and go home and then stop it when you get in the next morning. You need to kind of figure out what's the minimum number that you want to do. All right? And that's on the order of 20 to 30 iterations, I'd say, maximum. It can be less than that. Okay? So there's another process, though, called the iterative Fourier reconstruction. All right? So back projection, the radon transform applies everything in radon space, or kind of real space, quasi-real space. There's no Fourier transform involved. But now let's go to, I said there are new algorithms that can take care of these problems that I said exist with doing direct Fourier interpolation, okay? And that's these iterative Fourier reconstruction techniques, which you'll now read about now in the literature. This is what people are talking about. So what you do is you take your experimental projections, you put them in Fourier space by doing the Fourier transform, right? And you start this iterative process where you try to reconstruct the object in more places, right? You have more pixels in your reconstruction, especially between your projections, right? These red areas where you don't have any information if you start, right? And so from that Fourier transform, we can inverse Fourier transform. And let's say we figured out the interpolation problem. We can apply some constraints, right? We can say voxels can't be negative. There can't be negative density there, right? Or you can say that I know my object has a certain size, if you know that a priori. And you can say 0 everything outside of that. Okay? So those are some of the constraints you can do. Then you Fourier transform this three-dimensional object again. And then we get more information. We actually have information on all these voxels that we didn't have information on before. We take our experimental blue projections and we insert them where we know those are quote unquote perfect measurements, or the best measurements, not perfect, but the best measurements we can make. And then by doing this iterative loop, these red parts of our reconstruction will try to match the blue parts of the spectrum. So this iterative process allows you to make your three-dimensional reconstruction match as well as you possibly can to your original projections. Doesn't mean it's right. It means that it matches the original projections. Okay? So you might have heard a lot about equally sloped tomography, which is what we used originally to start doing atomic resolution tomography. And this is different in that you don't take images where you have a 1-degree tilt angle between every single projection. That isn't good. When you interpolate from the real space, which is r theta, to Cartesian space, which is xy, right? We have a problem. How are we doing for time? 9:30? Half an hour. OK, good. Half an hour? Or 15? Or 20-ish minutes, right? Anyway, OK, I'll take a half an hour. OK, so yeah, that's fine. So reciprocal space, remember we were taking our images at equal angle increments. 0 degrees, 1 degree, 2 degree, 3 degree, 4 degree, right? But we don't have to take our projections on that. We can make our goniometer go to any projection angle that we want. So why are we doing that, right? So it's this clever technique where you actually match your projections, where you acquire your projections, the tilt angle of that projections, to what's called a pseudo-polar Fourier transform. Okay? And I'll talk a little bit more about this and kind of the idea behind it. But instead of going 0 degree, 1 degree, 2 degree, it's kind of 0 degree, 1.1 degree, 2.5 degree. There's a set of projections that you take your data at, and it's on this pseudo-polar grid. Okay? So we're going to match instead of trying to match the reconstruction algorithm and make that conform to our data, which in some cases has its own limitations, we'll make our data match to the reconstruction algorithm. Okay? And so then if you take your data in this very kind of clever way, you can use what's called a different type of Fourier transform called the pseudo-polar Fourier transform, where there's no interpolation between real space and Fourier space. Okay? So your real space grid then has this transform that you go back and forth. You don't have to do really any interpolation. Okay? And so you can do this iterative loop without introducing artifacts based on your interpolation. Okay? So we have an n by n Cartesian space in real space, and we have 2 n projections at plus or minus 90 degrees. What this is called equally sloped tomography, because now we don't do equal angle. We take all of these different projections have the same slope difference between them rather than equal angle. And that gives you a different set of measurements. Okay? So these lines lie on a set of n concentric squares. So you see each one of these is on a different square, right? And so you make that line go through all those measurements on the square, where the distance between each measurement, right, has the same length. So this is different. Normally you think of this in terms of polar, but now we're going to use this different clever way of doing this, okay? So this pseudo-polar FFT is inverse and technically exact, right, although our data is not. And it has a very similar speed to the normal Fourier transform. So that makes it very fast. So the idea behind this, it's called equally sloped tomography. That's the word, the name that we gave it. But it was an older concept that was from a long time ago in 1987, and maybe was used in X-ray for more things. But instead of doing polar coordinates, which you're more used to, you do what's called linogram coordinates. So instead of a set of concentric circles, you have a set of concentric squares, and you take the data according to those concentric squares. Okay, so it's equal distance along each square between points, whereas in here you'd have equal distance along each circle. So you can see the difference between those two, right? And that subtle difference makes a big difference in how you can do the reconstruction. Okay? So generation of these EST angles, this is the equation that you use to do it. Okay? And you just type this in maybe to Excel. Just make sure that you get the equations right, the tilt equations right. And this is kind of what it looks like. For each different tilt number, this is the angle that you take it at. And you just want to do those as close as you can to those different angles. And then you can use the EST, this iterative Fourier reconstruction, to get a better reconstruction in general. Okay, so you usually use n is 2 to the x. So you use maybe n to be 32, 64, or up, or up, or up. Okay, so this is the number of projections that you take. 32 projections, 64 projections. The next one would be 128. Okay, so you probably will end up in this kind of range if you do that. And so as a comparison with just a simple back projection, this is telling you how much information we have. So higher is better. How much information you have at each spatial frequency. And so doing EST, where your signal to noise ratio is infinite, you have perfect projections with no noise, you can really beat the weighted back projection significantly, and other iterative techniques as well. But if you have some noise, you can still do better. So even though this maybe doesn't look like a lot, but that's a better reconstruction. Okay? So the idea of this really is that you match the acquired data to the algorithm, and the algorithm will be able to more faithfully match the reconstruction to the original projections. You're not kind of limited by what the algorithm can do. It tries to do it as well as it possibly can. Okay? So it's not magic. It's not like just because you take images at these different equally sloped tomography, it's not how you take the data. It's that you can then use that data in an algorithm and they match very well to each other instead of trying to get around the problem with the sampling. Okay, so these advanced iterative Fourier algorithms, EST is only one type of these. There's many more, and we're even going beyond that now. So you, as I said, just to reiterate what's going on, you acquire the data on what's called a linogram grid, and that allows direct iterative Fourier inversion. It allows you to incorporate constraints into the reconstruction, which is a little bit easier for the computer to do that when you do this in Fourier space. You can apply constraints in Fourier space, for instance, which you can't do when you do a radon reconstruction. And then this attempts to calculate the best match between the reconstruction and the experimental data. And in general, it gets a better match than the back projection methods. There are more newer algorithms provide similar or even improved fidelity of the reconstruction. There's a recent paper we have where you take this another step forward, and the angle requirement is significantly relaxed using this new GenFire algorithm, and it allows for optimized angular alignment also. So if you take your projection at 1.1 degree, but the algorithm thinks it's 1 degree, then that's an error, and it can actually search for what that best angle is. It's hard to do, but it can really improve reconstructions if you need to get to that last bit. It's very similar to what the cryo-EM people do. There's also things called compressed sensing, which is kind of a buzzword. They're not really using it the way that compressed sensing in the traditional mathematical sense of the word is, but it is useful to talk about and useful to get reconstruction from. So it's improved reconstruction from noisy. What the goal is to get improved reconstructions from noisy or fewer projections, which just means lower the dose. You want to go to lower dose, faster or lower the dose. But you require some sort of sparsity condition. It means that the way that you take the data or the way that the data is acquired, you don't have all the data, which seems the opposite to what you want to do, but you actually want to make it less of the data. And so you're kind of using these different mathematical formulations like the L1 or the L2 norm penalization, which is really penalizing differences in the reconstruction between voxels. That means it's highly unlikely that you'll have a 0 and a 100 right next to each other, right? Objects just don't really work like that, okay? Or you're kind of penalizing the square difference between things, so it's similar to CERT to other types of things. And there's also what's called TV minimization or total variation minimization. And that's really kind of enforcing smoothness, but at the same time edge preserving, which seems very counterintuitive also. It's very similar to like not similar, but it's a median filter would do the same thing. But there's a way to say that at the edge, keep that edge, but things that are very close to the same, just make those smooth. And that is how your objects kind of are at the nanoscale. So this works very, very well. So you'll see a lot of new papers on these new types of algorithms, which are very exciting. And then I'll talk about a completely different kind of reconstruction technique that people are pushing in order to get to atomic resolution, right? So we have these, what you can look at is this object. You can assume that atoms are discrete, right? We don't really care. Nuclear physicists care what's inside the atom, right? But the basic building block of material science is the atom. We don't really care what's inside the atom as much, right? You care that that's a titanium atom, or you care that that's a type of atom. Although you might care about the bonding, but for structure, you don't care about the bonding as much, right? So we just need to know where all of these atoms are. So that's actually a lot simpler problem, because if you just assume an atom is at a certain position, that's very sparse, right? You have just an atom at one position, and none of the other voxels around it really matter, right? So that's a different type of information, a different description. Instead of a description of x, y, and you have an intensity at every position where the atom might be there or not, you just have a list of this atom is at xy coordinate. So that's a very different type of data, right? So that's what they're trying to get using what's this discrete atomic scale tomography. So you can link the exact shape to these size effect phenomena. So that's why we want to get down to atoms. You need to access at least 3 zone axes in order to look at this object and say where all the atoms are. And ideally, you want them sharing a plane, like one great circle of rotation. And so that's kind of a 1xx kind of plane, okay? So you could do 1, 2, 2, 1, 1, 0, 1, 0, 0. Those are the kind of measurements that you need. And you utilize this discrete nature of crystals in order to figure out where all the atoms are. So it's a direct, you do basically, you take your direct projection of that object along one tilt zone axis, and you take that intensity and you turn that into a number of atoms in that column, all right? Which in and of itself is pretty difficult. But the idea is that if you reconstruct things, if you sum along this direction, if we have this matrix where we have 1 where there's an atom and 0 where there's no atom, if you sum along here, you get there's 1 atom in that row. Here we get 3 atoms. Here we get 5 atoms, okay? But if we do it along many different orientations, right, we can figure out that along this direction, you can figure out how many are in this row, in this row, in this row. So each projection along a different direction gives you a different number of atoms along that direction. And so inverting this is just linear algebra, pretty much, right? So people have been doing this by doing quantitative HR STEM. And this is from LeBeau's paper in 2010. This is now pretty old. They're doing things far beyond this. But this was kind of the first idea about that, or the first real demonstration of that, where you can take these atoms, these columns of atoms. Remember, when we're looking at our object, we're not doing atom column resolution, atomic resolution. It's really atom column resolution. You're looking at a whole column of atoms at atomic resolution. So you can take the intensity in these, and if you are very careful about how you measure that intensity and how you match it to simulations and how you set up your whole experiment, it's not trivial, you can kind of count how many atoms are in there under certain assumptions. So they did that, and they can put these atoms in these different rows, and each one of these is kind of the cutout of each atom. You could see they all have pretty much the same intensity, right? And so then by doing this along many different zone axes, at least 3, you can then use kind of this linear algebra idea in order to then fill in the reconstruction where all the atoms go. Okay? And this was recently applied to 3D nanostructures. This paper only showed how you could count these atoms. And then I'll show a little bit of the details of that. So if we go back a little bit, a reconstruction review. So everything that I just told you, I need to tell you again, right? So back projection is a real space operation. There's no Fourier space. By real space, I mean there's no Fourier space. You use radon space, which has a simpler interpolation. It's generally faster. It's much simpler. It's available in all the codes that you'll generally use. Okay? And for most people, this is good. This is good enough. You don't need to go much more beyond this. So weighted back projection means that you do this back projection, but you use an R weighting in Fourier space. So you're overweighting. When you're doing the reconstruction, you're overweighting the low frequencies, underweighting the high frequencies. So you just use a filter that does the opposite, R weighting, distance from the 0. These iterative techniques compare each reconstruction. Because you have a model in your computer, you can either slice it or you can project it along any angle that you want, right? And you compare those assuming your original perfect projections, all right? And by doing that, you can take artifacts out of the reconstruction that shouldn't be there, which if you were to look at the projection and look at your object, you say that shouldn't be there. So the computer does that for you. Okay? And that's the CERT reconstruction. More advanced algorithms are definitely now available. This discrete iterative Fourier inversion, which I talked about. Discrete tomography and atom counting. And then there's also a lot of compressed sensing. They actually use some of this compressed sensing in discrete tomography also. But this can be used, this has been used for low loss EELS maps and trying to figure out plasmons. And it's a pretty interesting technique. I think they named it the wrong thing though, a little bit. So tomography artifacts and limitations. Where are we limited? And why are we using STEM versus TEM? Where would you want to use STEM versus TEM? So STEM has its disadvantages and its advantages. It's a little bit before this talk, it was a little bit less ubiquitous. Now it's becoming almost everything is a STEM these days, STEM, TEM, or just a STEM. But this, if you have older microscopes, it might be more difficult to get a high quality STEM that can get nanoscale or about angstrom resolution. That can be a little bit more difficult. The TEMs are kind of more generally available. This is becoming less so though. A scanned image takes about 30 seconds to acquire, 10, 30 seconds. And remember, we have to take 70 projections, maybe 140, right? If we do plus or minus 70 and we do 2 degree or 1 degree orientations. So every minute that you add to one step in your tomography acquisition adds an hour and a half to the whole thing, right? So you want to get that down as much as you possibly can, and the scanned image is already around 30 seconds. So that's kind of a problem for how long it takes. It's very sensitive to defocus. If you're a little bit out of focus, generally it's not as sharp of an image. And there's different scales to that. There's contamination also. That's the worst thing in STEM. It ruins so many experiments. And so if you start seeing contamination in a tilt series, just give up. That's it. I mean, you can have a little bit of it, but if it's really big, just start over. Try to figure out, get rid of that contamination, because that builds up over time. Your images at the high tilts or lighter get much, much worse, and your 3D reconstruction is just significantly worse. Okay? There are some things you can do to kind of get rid of this, but getting rid of it and solving the source is much better than trying to solve it afterwards. Okay? It's an incoherent imaging method, which means we can use it for crystals because they don't like change as you tilt. You get very high contrast, especially for heavy materials, so it works really well on metals, nanoparticles, things like that. It's not very good for very light things, right? And then it's multimodal. You can do EELs at the same time. You can do EDX at the same time. You can take HADF, ABF, bright field, EELs, EDX. You could do a tilt series taking all of those at exactly the same time and do a reconstruction, putting all of that information together with many channels, right? And even more as we go towards more advanced detectors. So for parallel beam, it's more common, I would say. It's single shot imaging, so it's 1 second per image. Relatively insensitive to defocus because you have to defocus to get contrast. And it can be extremely low dose. But the problem is you get this complex phase information transfer function. So in some cases, especially with crystals, it's not useful at all. You no longer are working with the projection requirement. For low contrast things, you have to use a large defocus, which is not great, but at least you can see it. And you may require CTF, what's called CTF correction, because as you tilt it, things at different focus will have different CTFs, and that's a problem. Okay, we also have a problem of STEM depth of focus. So although you might look at this and say, my whole thing's going to be in focus, this is actually what the depth of focus looks like if you have a fairly thick sample. Okay? And so the focus beam has a finite depth of field, and for an uncorrected microscope, you have maybe a 20 nanometer depth of focus if you're running it in high resolution mode. If you lower your convergence angle, which usually you wouldn't want to do if you're doing high resolution, you can actually make this much, much longer. So in a lot of cases, you don't want to go towards these corrected microscopes, because this has only, at 100 kV with a 35 milliradian convergence angle, you have only a 6 nanometer depth of field. So that's not useful for most tomography stuff. Okay? So in general, I want to say a corrected STEM is not always better for electron tomography. A lot of people say, I want to use your corrected microscope to do tomography. I'm like, no, you don't. Okay? A normal electron microscope is probably good enough for most people. But you really have to think about this depth of focus issue. So the data acquisition for a tomography holder, you need a nice tomography holder that you can tilt up to high angles. And just, this is just, I'm just introducing this kind of concept that you can't really tilt. There's a reason why you can't tilt plus or minus 90 degrees. And that's because your holder will be in the way, right? You can't project through the whole thing unless you have a needle sample. Needle samples are really hard to make, though. And the reason, part of the reason also is you have this what's called the pole piece gap. So these are where your electron lenses are, the objective lens, and you put your object in between those lenses. And so the distance between these lenses kind of gives you a maximum tilt range that you can have. So in some cases, you need to get a special holder, a tomography holder. You should really buy a tomography holder if you want to do tomography, because normally you might only get up to like 30, 40 degrees, but you can get plus or minus 70 degrees, 80 degrees, which is the limit of the goniometer in the FEIs. You can get all the way up there if you have everything working properly. Okay? But the missing wedge is a problem, right? So I'm going to talk a little bit about what is the kind of theory behind that. I have to get back to theory a little bit here. So the missing wedge and artifacts of that. So I like to call it the infamous missing wedge, because everybody's heard about it. But what does it actually do? So sample geometry limitations, the sample geometry limitation, which is what I just told you, we're projecting through an object, but we can't tilt it to 90 degrees in most cases. Almost every object you look at is going to be this. If you have these new needle samples that you can make with fibs now, you can get around this. And the problem is we're going to have this missing wedge of information. It's not only in, a lot of people will just show you the 2D part of this, but you have to think it's along this entire axis, okay? So it's a pyramid, like a square pyramid along the whole thing. So it's a lot of missing information. You might worry a lot, but you do have a lot of information here, right? Okay, so the effect of the missing wedge is that from Midgley and Whalen's paper back in 2003, this is well known, and using this kind of phantom, you can see exactly by using back projection or weighted back projection, we can see how if you don't have a lot of information along the projection direction at these very high tilts, you get this elongation, right? So that's where that equation at the beginning of the lecture gives you this kind of elongation object. And so things that are near each other are kind of elongated, and they mix together along the projection direction, because you don't have information about that object, OK? But a lot of things that people are doing now are kind of looking at these nanocrystals, and they want to look at facets of these nanoparticles, OK? So faceting on a nanoparticle is really important for catalysis, for how they work. But tomography has some interesting effects, theoretically, on that, OK? How does this affect the shape of this? So let's do reconstructions where we're just looking at a two-dimensional object, and I'm projecting it always along the vertical direction. And what I'm going to do exactly the same simulated reconstruction, where I start with my object at 0 degrees. Let's say it's perfectly sitting on a substrate like this. Or let's tilt it a little bit, 15 degrees, 30 degrees, and 45 degrees. And let's see how the missing wedge affects the shape of this object, OK? And I think you all guess where this is going, I think. So this is our projection of this kind of core shell nanoparticle I made up, right? And you can see that we don't get very good reconstruction of this facet, but really good reconstruction of this facet. So if you didn't really know where in space your projection, your original projection direction was, or where the missing wedge was, you might not be able to make a measurement or figure out what this object really looked like, right? And this is with, I think, plus or minus 70 degrees. So we're missing this information really, really badly. This is the information we're really missing, OK? If we tilt it, though, we can see these start blurring a little bit, but we start filling this in, right? And if we tilt it more and tilt it more, this looks like a really great reconstruction. But this and this were exactly the same experiment, just the object was oriented in the microscope slightly differently when we started, OK? So this is the kind of stuff that you should look out for, these artifacts, when you're doing reconstructions, especially of faceted things. So here, if we take a line integral along these different directions, we can see that we have no idea where the edge of this thing is. And we have a pretty good idea where the edge of these things is, right? So we can measure the thickness of this shell pretty well and where this interface is, right? So this 45-degree rotation gives good results for this faceted object. But you have to be very careful about what you're looking at, right? And the reason why I did this was I had some reconstructions of these platinum palladium core shell particles. And the reconstruction of the object looks very similar to the reconstruction that I did in simulation. So I wanted to see why do some of them look blurry in certain directions and why not, and what's the kind of limitation of that, right? So always keep in mind the direction of the missing wedge. And I've kind of advocated, I think, a little bit there. If you're showing a reconstruction in a paper, you should kind of show where the missing wedge is. That would be really useful to people. OK? And now the grand challenge of 3D atom is 3D atom tomography. I have to talk about this a little bit, but I think maybe I don't. I have maybe 5 minutes or something. Oh, I'm already over. I have 7 minutes. OK, that's good. I had time for questions. OK. So I don't know, some minutes. So Richard Feynman, he gave this famous lecture, which basically started nanoscale stuff. It would be very easy to make an analysis of any complicated chemical substance. You just have to know where the atoms are. As I said, the building blocks of materials are atoms. OK? So this has been a grand challenge of material science and biology for a really long time. They just want to know where the atoms are. Then we can figure out the structure of the object. And from that, we can figure out what it does. Why does it do these various things? OK? So we want to look at dislocations, point defects, dopant atoms, core shell. No one can see what the interface between a core shell particle looks like, because it's around in 3D and it's at the atomic scale. So how do you even look at that? Glass transition, ultimately amorphous materials, right? So I just want to say where I started and now where we are these days. So this wasn't the best tomography reconstruction. I'm just saying that this is where I was back in 2006 when the original lectures were. And I was showing this kind of stuff where this is 250 nanometers. And now we're showing, using the aberration-corrected microscopes and advanced reconstruction algorithms, this is an iron platinum nanoparticle where we measured the position and type of the atom at every single position. So it's come a long way. OK, so doing STEM electron tomography, there are a bunch of different ways to do it. I talked about discrete tomography. There's kind of compressed sensing and discrete tomography kind of put together. And then we're using this equally sloped tomography to use this iterative algorithm. All right? And so I'm going to talk a little bit about this because that's what I know a little bit more. And why do we want to do this? We're directly measuring defects, like in graphene, on two-dimensional surfaces. You can do that with STM, scanning tunneling microscope, very easily. And by doing that, you can figure out what are these defects, and then you can say exactly how those defects, by knowing where all those atoms are, you can do DFT. figure out how these defects affect the functionality of the material. But this is 2 dimensions, right? Not everything is 1 atom thick, although some people like to think that. Okay, so the first thing we did was 3D atom displacements in tungsten. It's kind of a boring sample, but it ended up being really interesting. So you can look at all of these atoms, and each one of these atoms is colored by the height of the atom. And then here we can look at the atomic displacements in every single layer of that. And then we can also say that we found a missing point defect here. So if you look at the density as we change this 3-dimensional reconstruction of this object, if we change where we set our density to for different intensities, we can see that we have no intensity at the center of this. So that's a point defect there. And then this is the more recent iron platinum. So looking at the position and type of every atom allows us to look at the different grains of this object. So we can blow this thing apart and look inside the object, right? So we can tell that there's L12, L10, different types of grains in different positions, and that we have these 2 kind of interlocking grains on each side, right? And these different grains give very different magnetic properties. These particles are what are being used in the next generation of hard drives. They're trying to figure out how these defects and how these grains affect that. So that's why you want to do this kind of stuff. So there are other people doing this, like Sarah Balls in Europe, and they're doing this kind of atom counting and 3D reconstruction. We have to take 64 projections, or many projections, which is very dose intensive. It doesn't work for everything, or many things even, I'd say. But they're looking at a few projections along a few different orientations, and they're also using a low resolution tomography to fill it in with atoms afterwards. Okay? And they're doing this atom counting technique. There's other things where you can do just a single projection, 3D reconstruction, and that's using TEM. TEM is extremely sensitive to how many atoms. And if you do everything very, very precisely, with an aberration-corrected microscope, they do exit wave reconstruction. Actually, this was just a single image. But if you set up your microscope very, very carefully, TEM is a little bit harder to do. But it's not trivial. But you can kind of figure out how many atoms are in each row. You can figure out the height of those atoms, not just how many atoms you have. Because if you have 10 atoms here and 9 atoms here, you don't know if they're like this. You don't know where it is, right? But from TEM, it's very sensitive to small shifts of the atoms. And then you really have to talk about cryo-EM. It's becoming this huge field now. It was big, and now it's becoming bigger. This is going to solve a lot of problems. And in fact, it was the 2015 method of the year. Okay? It's really worth looking this up. This Nature Methods, it's a really cool way of doing electron tomography. Totally different. It's a whole separate field I didn't even touch on. Okay? So these are my acknowledgements. I got help from a lot of different people here at Cornell and here and at UCLA and at UC Berkeley and at University of Birmingham. And then I just want to also put up some resources. So if you want to know a lot more about tomography, I only had an hour and 15. I think I'm right on time. There's so much more to know, and I went through a lot of stuff maybe a little bit fast. But TomViz we're going to talk about later. There's many different reconstruction packages that you really want them to be parallelized. It's embarrassingly parallel, so you can get a reconstruction relatively fast. I wrote a recent review article on doing hard and soft material tomography, so that's actually very useful. And we're going to give a workshop and short course very similar to this, but all on tomography. That's going to be in October in Berkeley. So October in a lot of places is not that nice. Berkeley is very nice. So registration is open for that as well. So I had to at least plug my own thing there a little bit. So I'm all done, and so now I'll definitely take any questions that you guys might have.